So, good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium, not on a Monday, and I think I put your laptop on mute. Otherwise, I can hear me from here again. So this afternoon, it's a really big pleasure to introduce to you Professor Sir Nigel Shadbolt, that hopefully all of you might know, because probably 5-6 years ago, he wrote a very popular, interesting book, yeah, called The Digital Ape. Yeah, so please, if you haven't read it,
oh, it's essential reading.
Read it. Yeah. But Sir Nigel spent probably most of his academic life studying various aspects of artificial intelligence, and he was always very interested in the human-centric aspects of AI, if I can say so. At the moment, and that's the reason why we were lucky to have him with us today. He's at STIAS, yeah, for I don't know, 6 months probably, or the first half.
Sadly, 3 months.
3 months, okay, at least
the end
for
of this week.
enough to to have you give a talk.
Yeah.
So thank you very much for that. But when he's not at STIAS, he's the principal of Jesus College in Oxford and a professor of quantum computing at University of Oxford. Yeah. He was also involved from the very beginning with the Open Data Institute that he co-founded with Sir Tim Berners-Lee, yeah, that all of you know from the famous internet stories. Yeah. And roughly 10 years ago, he was knighted for his contribution to services to science and engineering. Yeah. I think I could go on for a long time to list all his achievements, yeah, but they are on the announcement, so I assume that human intelligence can still read. Yeah. So Nigel, thank you very much for accepting our invitation. We are really happy that that you're here with us today, and you're most welcome to start your presentation. Thank you very much.
Thank you. Thank you. Thank you. Okay. Well, you can hear me okay in the audience. That's fine. Good. So it's a huge pleasure to be here today. I'm really providing some reflections on our understanding, the trajectory of our understanding of large language models. So this isn't going to be a detailed technical exposition on transformer architectures, which in particular underpin many of today's systems. We will look at the technical limitations, but I also want to really spend time talking about what it would take to understand them in general terms. So I'll describe them in general terms and what it's going to take us to understand these large language models, their capabilities and their potential limits. So I'm going to go back to I'm going to go back to a moment in 2020. We had I asked by James Monica, who was then the head of Global McKinsey's Institute on AI, and is now a senior vice president at Google around AI and society. I've been asked to contribute a chapter to a book that was revisiting the history and development of AI, and it's a freely available collection of essays that I would recommend. It's extremely interesting. My paper looked at the history of AI and how it was evolving. And actually, I deliberately used this wonderful phrase from Darwin's Origin of Species. Right at the end, he talks about from so simple a beginning, wonderful forms are being continuously evolved, essentially. So he's looking at the evolution of life on Earth, driven by the principles of, as we now understand it, genetic inheritance. And of course, he didn't have that model at the time, and the natural selection. So I was looking at this and reflecting on the fact that in many respects, Darwin's original work assumed a last universal common ancestor. And if you think back to what that might even look like in our own field, of computer science. What is that? Well, computer science we can trace back, I think, to some of the extraordinary seminal work that Alan Turing did. His 1936 paper, published in the London Mathematical Society's Proceedings, really laid the foundations for computability, for computation as we understand it. Of course, he then went on in the war to do extraordinary work, realizing his considerable abilities in cryptoanalysis to build an electromechanical computer, effectively the bomb, to decrypt the Enigma intelligence signals from the Germans at the time. After the war, and many of his contributions in this area, they were not recognized because all of that work was kept under the Official Secrets Act. Those working at Bletchley Park and many of the advancements made in computing, because in fact, the Colossus machine which followed BOM had many of the characteristics of a modern computer architecture, were not acknowledged, and in fact only became acknowledged late in the 20th century. In 1950, he published a paper in a philosophical journal called Mind on computing machinery and intelligence, where he famously posited the imitation game, can be known as the Turing test. There's a wonderful picture of him here with the Manchester Mark I, a machine that had all the characteristics of the modern computer. The interface was essentially an oscilloscope, but he was already imagining a world in which increasing compute power would lead to precisely the challenges we now encounter as we think about whether or not modern machine learning architectures could be described as heralding artificial general intelligence. So just 6 years later, and tragically in that time, Turing was dead. He died apparently by committing suicide following a really quite awful set of circumstances in his life, but still doing extraordinary work, both in computing, in theory of embryogenesis, all sorts of great work could have followed on from Turing. But in 1956, a group got together, the famous Dartmouth Conference, which coined the term artificial intelligence. And there are a relatively undiverse set of individuals, one could say, but remarkable nevertheless, basically proposing that we could understand intelligence through its formalization in computational devices. A formulation that became dominated by the work of people like Simon and Newell. This term, this general phrase, the physical symbol system hypothesis, was the notion that explicitly manipulation of symbols was sufficient in principle to actually account for all of the intelligent behavior you could see around you. Well, that in turn, I think, was one of the reasons that the dominant paradigm in the early decades of AI was one we came to call the symbolic tradition, and in particular one rooted in logic and theorem proving. So explicit mathematics based around explicit representations of the world. And a great deal of the AI techniques at the time relied on a set of techniques where the challenge was to incorporate and model the world as a set of logical propositions. Those techniques, together with techniques that developed in search, particularly searching very large game trees, techniques in the domain of planning that allowed you to construct symbolic sequences of actions to achieve goals, really did comprise the early years on decades of AI. And one has to say, really quite successfully. I mean, the very earliest systems that could plan and recognize language, there's Terry Winograd's famous system that could interpret simple language queries, execute a series of plans in a simulated world to actually demonstrate what appeared to be really quite flexible adaptive behavior. On the other hand, we had increasing compute power. The exponentials of the compute world led to one of the first kind of original shocks of AI, and periodically, about every 10 years, you'll see this hyperbole around AI. It's going to take all of your jobs. You're going to find yourself having your scientific basis revolutionized. You are going to just anytime soon be surrounded by super intelligent machines. Gary Kasparov there holding his head in his hands when he was beaten by Deep Blue. Deep Blue that was searching around 100 million to 200 million positions, board positions a second. Okay. Now, clearly not a way that humans play chess, but nevertheless, this increase in power and techniques that could do heuristic evaluation of board positions with large databases of end and final game positions led to a quite extraordinary accomplishment. I would just note on the way, it didn't lead to the death of chess. I mean, modern chess enjoys as much success and enthusiasm amongst human players as ever. We now have new forms of chess, hybrid chess, where humans and machine teams team up together. Machines are used to help augment chess playing and human chess playing. I think this is actually a great model for how we can see AI being used in the future. And I make these framing comments really because I do spend an awful lot of time trying to dissuade people from the apocalyptic view that the machines will simply do away with us, wake up, and actually we're already redundant. Okay. The kind of AI that my early part of my academic career was involved in was very much in building decision support systems. This is a system which can lay out in 3 dimensions from a process specification sheet, a plant to manufacture a chemical product. Effectively, this is kind of a graphical logical specification for producing a product. A chemical engineer would understand that. Machines couldn't at the time. We built a system that could. Using a variety of rule-based reasoning, constraint-based reasoning, we were able to lay out these kinds of architectures. Not straightforward, actually. It took a lot of engineering to build these systems. A very interesting point here is that there are pumps. These are the reference symbols for pumps here in various parts of this diagram, connecting various components together. There aren't in other parts of the diagram. Only way you could make this system work is to put these tanks above these receivers, because you're going to use gravity flow to get the liquid from one place to another. That is not in this specification. It's part of the common sense principles that all chemical engineers embody, a kind of a naive physics. How do we encode that? And it's, again, going forward, one of the challenges we find in AI is this incorporation of what we might think of as common sense reasoning. Come back to that. Okay, so lots of work spent trying to build those kind of systems. When the web came along, I myself spent a lot of time building, if you like, systems that could scale at web scale. So you'd put small amounts of AI into the web, small amounts of knowledge representation, small amounts of reasoning. We thought that was a particularly powerful way of connecting data, building a web of data, using this whole set of elaborate machinery, so-called ontologies, controlled vocabularies. Actually come to be very widely used in science. So many people working in life science, for example, genomics, will use tools like gene ontology. They are effectively systematic representations of the way in which you choose to structure the world and organize it. And in structuring worlds in terms of hierarchies and networks of various sorts, you can apply a variety of reasoning techniques to them. Symbolic, explicit reasoning techniques, which are also transparent. I also spent some time with Tim Berners-Lee opening up the data that would be represented on the web, particularly important data, it turns out, for the kind of modern machine learning tools we have, which have devoured huge amounts of the data on the web. And as we built data, liberated it, we were building essentially a very large network of connected data assets. And I think it's worth saying, as well as I kind of just wrap up on this kind of first part of the talk, it's often thought that somehow good old-fashioned AI, the AI from the 60s, 70s, 80s, 90s, has failed. There's a huge amount of tooling and methods out there which have yielded real results across the board, from graph theory to algebra to the examination of mathematical constants, to various proofs in knot theory. This is a color theorem here that was proved in part with machine-assisted proof. So there is plenty of technology out there to support a style of machine-based reasoning. Come back to reflecting on how that will still turn out to be important in an age of neural network systems and machine learning. I had almost been interested in neural networks. In fact, this was work that I did with a colleague with very small little robots, actually implementing a biologically inspired theory of how synapses connect, how neurons connect in a small network. We were interested in building biologically plausible systems. That this has a very nice feature. This equation is telling you how you strengthen connections between synapses, depending on whether or not a particular, in this case, analog for a growth hormone is secreted. This kind of Hebbian principle based around real biological principles turns out to be very interesting. So you can show in biological systems where these brain-derived neurotrophic factors which promote growth, where they're suppressed or missing for various reasons, these networks don't form or they form inappropriately. They are activity-driven, activity-dependent, and you can get some very nice features out of these systems is that they will take their neural networks, small neural networks as they were at the time, these were only running on small chips, and customize the network to the precise characteristics of the individual robot. In the real world, this robot has a range of infrared sensors, not all of which have the same precision and tolerances. The wheels wear at different rates, their motors aren't exactly balanced. So if you want to build a system with simple behaviors to move towards certain objects, avoid others, be phototaxic, that is, respond to light or other kind of stimuli in the environment, these kinds of networks with these kinds of principles build a neurology suited to the morphology, okay? Which I think, again, we thought was an interesting and powerful insight and is exploited quite widely in modern robotics. So to say AI is a large set of techniques. Over here, we'll be looking in more detail at the elements of the deep learning that is used nowadays, but from search to logic to knowledge-based systems to knowledge representation methods, these things are together hugely powerful. So neural networks, we know something about neural networks. We know essentially these connected networks can be organized according to different architectural geometries. They can be organized to reflect different network topologies. And the crucial question is how you pick particular architectures to suit particular problems. Historically, neural networks have gone through a number of stages of development, often the hardware constraints of a particular era. So parallel distributed processing or neural networks were widely promoted in the 80s and 90s. The actual compute power available meant that there were severe limitations on the size of those networks, the depth they could actually affect to. Those have been removed as we've gone through this extraordinary set of exponential increases in compute power. So let us just spend a little time looking at the history of one strand of machine learning. I want to get us eventually into the area of large language models. Right back in the 1950s, approaches to how natural language could be processed and understood included statistical methods, bag of words, recurrent neural networks in the 1980s, various forms of long short-term memory models, different ways of thinking about how language could be represented and encoded in network structures. One of the, I would say, breakthrough moments was in 2013 when the word2vec algorithm and approach was developed, in which previously an awful lot of natural language processing had operated essentially by trying to encode language understanding using grammar-based rules. It was very influenced, in fact, by the linguistic theories of people like Chomsky and others. You had a grammar, you had a dictionary, you had a set of well-formed formulas or sentences, and the job was to try and work out how to generate appropriate structures with appropriate semantic meaning from those assets. It was always difficult to understand how you would encode for semantics. You could do it in the logic-based approach. You used a denotational semantics in which the words mapped into objects in a universe of discourse in a world directly. But the great insight of Word2Vec was to re-represent the problem fundamentally, to understand that if you encoded a word as a vector, and if you then looked at the natural distribution of words in language, in books, in the text you had available, you could begin to build high-dimensional spaces in which those vectors clustered. You would get natural co-occurrences of words, for example, which shared meaning. The subsequent evolution of network architectures to exploit that insight has been very dramatic, and one I will pick up on here is the transformer architecture. Here. So only in 2017 did this idea move into view. Effectively, that the fundamental objective was to take a very large corpus of training data with the objective of simply learning to predict the most likely token, so-called auto-regressive sequence-to-sequence algorithm. This is quite an interesting diagram. This is from Jan LeCun. It actually shows you back to the kind of natural history analog, the kind of Darwinian species tree. He kind of tracks out the actual evolution of various types of transformer architecture. And some of these, of course, very much systems that we've become familiar with, whether it's GPT, back here, Bard, which was a version of Google's search engine. All of these things are rapidly deprecated or moved on, or another kind of system deployed. And we'd like to understand a little bit more about how that works. And just to say, if one takes the kind of GPT large language model as canonical, effectively GPT-3, many of you may be using 3.5 or 4, if you pay your money. GPT-3 feds with a significant amount of the web's content and simply is trained to predict the next word in a sequence, given its training. It's got word-to-vector encoding and positional encoding. It has a huge number of encoding attention spans and also decoder layers. Each layer, about 108 billion parameters, essentially settings in the network. So these are extremely powerful architectures. So powerful that in a paper in, gosh, it just seems so recent, but it was a 2022 paper, which already seems taken by events. This is the PAR model, Pathways to Language model. This was the Google proposed improvement on the on systems at the time. So what you're seeing here is a on this axis a preferred metric of effectively capability. We'll come back to how you measure this capability shortly. These are benchmark measures of capability. And here is the order of magnitude of the parameters of these networks. And at the time, what they were observing is there seemed to be an emerging power law on simply the size of these networks. And that was something that gave people real pause for thought. Also, this gives you an idea of where the original challenges in these networks were. It was trained on about 380 billion tokens. I say tokens because they don't actually chop up the training sequences into absolute words, but into smaller, computationally convenient tokens. And you can see that half of the data on which this system was trained were taken from social media. You can immediately see there could be problems with that. The problems were that you had to effectively detoxify the entire learned model. What is never talked about is the legions of individuals, many of them on the African continent, who spend their time basically poring over potential outputs to put, if you like, appropriate behavioral constraints around these systems, detoxifying them. Wikipedia, on the other hand, only about 4% of the data, but what ablation experiments have shown, and these are where you take a network and selectively remove parts of that network that relate as far as you can to a trained network, suggest is that 4% is highly relevant to the actual overall behavior of the system. So one of the questions we ask ourselves in modern large language research, large language model research, is what is the effect, what is the impact of different types of knowledge in the training phases of these systems? So moving on, no sooner is Palm out than GPT-4 is released. Extraordinarily large, we don't know exactly, but the estimation is that possibly as large as 1 trillion parameters. Very large networks. And of course, you'll have heard and be aware that this presents huge challenges, both to the companies who develop these, because they're very expensive to procure, but also to research institutions, to universities, to how do we begin to form the kinds of alliances where we can work with these very large platform companies to begin to access the very largest models. If indeed size is all that matters, and we'll come back to that. But here we can see essentially GPT 3.5 attainment levels on a range of benchmark exams that the thing was being tested against, as opposed to GPT-4. Apparently much better performance. So this notion that just the size of the actual network seemed to have an unreasonable effect on performance. The no sooner than GPT-4 than Palm 2. So this is, we're getting more up to date now, just in 2023. Again, interestingly, this Google system seemed to be performing better than the original previous system, and it actually reportedly somewhat smaller. So it may well be that it depends on a variety of factors to do with the way in which systems are trained, the way in which subsequently systems are fine-tuned. These systems can all be enhanced with their initial training, which is essentially on large amounts of data, subsequent reinforcement by human feedback, and a whole range of additional refinement tune the performance of these models to improve them in particular domains. And again, performance on tasks that have previously been thought to be very difficult. Language translation appears to be very impressive. And also something that had always been the holy grail but eluded traditional symbolic approaches to language. One of the challenges for many researchers in computational linguistics and in linguistics is the fact that many languages are underrepresented on the web. Many languages. Some languages very dominant in terms of the absolute representation of content. These very large models seem to have very powerful transfer techniques from seen to unseen languages, okay, or underrepresented languages. And exactly what it is that's been, in some sense, captured in the statistical regularities of the seen language that allows them to make very decent attempts at translations is, again, another area of active research. people who work on related language families, trying to work out whether there is something about those distances between different language types that allows the effects to occur. But very important to understand how this is happening. You get on to recurrent features of all of these systems. We need to understand their scaling properties. We are very dependent on software. Whilst people, this room may be familiar with some of the languages you use to kind of code these tools, when you're talking about the very largest systems, a huge amount of what makes them operate is simply the middleware that allows these very large distributed hardware processes to interact to one another. It simply isn't enough to have a thought that if you just buy all of this stuff and you implement a number of transformer architectures, you'll replicate what organizations like Google and OpenAI are able to achieve. And that middleware engineering is something that I think has to be recognized, and we have to understand how, again, we understand its impact. The benchmarks, I'll talk about benchmarks and we'll talk about some limitations now. And just to say, we wouldn't be where we are now without the extraordinary customization of hardware that has happened, that enables the representations that deep learning algorithms need to be supported. So deep learning algorithms have some very nice properties. They're very tolerant of reduced precision. That's not true of many numerical algorithms. Many numerical algorithms are going to require 32-bit or 64-bit floating point representations for numerical stability. Deep learning algorithms are generally okay with 16-bit floating point representations during training, and 8-bit and even 4-bit integer fixed point representations have been used during inference. So that's a very interesting trade-off that I don't think is often fully appreciated. So the use of reduced precision enables more multiplication circuits to be put onto the same chip than if higher precision multipliers were used, meaning chips can perform more computations per second. Computations needed for deep learning algorithms are almost entirely composed of different sequences of linear algebra operators on dense matrices or vectors, such as matrix multiplication or vector dot products. And that's led to the observation that making chips and systems that were specialized for low precision linear algebra could give very large benefits in terms of better performance per dollar. And that is what has led to things like the tensor processor that underlies Google's architectures, and indeed the NVIDIA chips that we see produced nowadays. And a good shout out for open source, I should say as well. I would say that normally. These tools have been super important in the development of communities and advances in the field. So benchmarking. Large language models use predefined tests or data sets to provide insights about their general capabilities. But there are limitations to these approaches. And I think it's important that we reflect on what they might be. There's a very nice paper, Beyond the Imitation Game, quantifying and extrapolating the capabilities of language models. So what do we want to understand there? So these are some, I can't quite, it's very small font, apologies, but these are the kind of sets of tests that our systems are subjected to. So this is a training set of benchmarks called Big Bench. It's 204 language tasks, and they cover everything from different languages, different topics, from verbal reasoning to reading comprehension to context-free question answering, different types of formatted evaluation method. So when I was showing those performance capabilities, they're against these key benchmarks. But as we know, all benchmarks are often constructed with potentially their own intrinsic biases, especially in areas, for example, to do with cultural or verbal reasoning. You can see these influences at play. And there's a lot of work going on to build more robust methods, whether it's reading comprehension or summarization or paraphrasing. But they have become the meat and drink of large language evaluation. So the challenge, though, is that these systems can lock you into a particular way of thinking about the performance of your network. They become very task-oriented. They don't deal well with out-of-distribution performance. They overfit. You can end up getting networks that overfit for the benchmarks. Areas like ethical alignment open up a whole set of additional kind of challenges that we might reflect on. So there have been attempts. Percy Liang at Stanford and colleagues have been looking at producing a more adaptive and flexible benchmarking framework called Helm. There are particular efforts to better understand how models perform on benchmarks outside of verbal fluency areas such as ethics and appropriate language responses. Theory of mind. So this is one of the things that we are always concerned with, I think, in our work. These sequence-to-sequence next token predictors, are they capable of extended reasoning? Good examples of this is the so-called kind of Salian problem, where basically things happen in the world, and unless you're an observer that can understand that a perspective that one individual has can be changed. Here, Sally puts her ball in the basket here and sees that, moves it, and is Sally surprised to find, where would she expect to find the ball at this point? And we all know that simple theory of mind, we make the right inference. There was a lot of interest around what kind of networks could or might pass this test. And extended applications of this have been a very active area of research. I should say that the simpler forms of this seem to be not too much trouble for these systems. But the question is, does that really reflect a notion that these systems can build a model of an interlocutor? Or is this a challenge of seen examples in training sets? So let's go to these systems, whilst capable, are also susceptible to error. And I want to spend a little time now in this part of the talk just talking about that. Endogenous error, outdated facts. Systems will be trained at a particular moment in time, and the world can change and move on. Now, of course, there have been adaptations to recent models to allow them to do so-called fact editing to keep their model the world current, but that is an ongoing challenge. The inference and reasoning failures that you can find, there are actually examples where, in spatial reasoning in particular, models can draw the wrong inference. Hallucinations and confabulation, famously, these models will sometimes make up material. You can ask them to generate plausible papers on a scientific domain, and not only will it produce the data to support the kind of task you might set it, it will even produce plausible looking references. And even the best models, you can't quite see it here. Yes. Okay, well, I can, by memory, I can sort of tell you, this is GPT-4. This is a benchmark that is maintained on hallucination effects. The essential task is, a company called Vectera maintained this, if you're interested. You feed the large language model a stack of about 800 short reference documents, and you ask the language models to provide factual summaries of the documents. As directed by a standard prompt. Now, you'll be aware that one of the alleged benefits of these large language models is summarizing huge literatures. Paralegals are out of a work, research assistants don't need to turn up anymore. It turns out if you prompt the system, you're a chatbot answering questions using data, you must stick to the answers provided solely by the text in the passage provided. You are asked the question, provide a concise summary of the following passage covering the core pieces of information described. Well, the summaries provided over the 800 documents, the very best performing systems will hallucinate at the level of about 5% of the content. And really quite capable models hallucinate at about 15 to 20%. I mean, so you really have got to ask yourself what that trade-off looks like. And people say, well, you know, why is that? What's going on here? How can that be? And of course, it is the fact that fundamentally, the architecture of our large language model is not a deterministic program. It's an autoregressive loop. It's a loop which merges the current input with the previously generated context representation. So that model of a traditional CPU, which is executing exact instructions, can be thought of in this case as a probability function. So I'm going to talk about some work that colleagues and myself at Oxford have been doing in this area. What we've been doing is investigating the extent to which large language models can simulate the execution of computer code and algorithms. Well, why would you want to do that? So this is part of a project funded at the Alan Turing Institute with colleagues at Oxford, Leeds, Technical University of Munich, and the University of Salerno. So the code simulation capabilities of large language models are an important object of study for probably two major reasons. First, large language models have shown some capabilities for planning, which requires both reasoning step by step and recursively dividing a problem into subparts. Second, code simulation requires a large language model to turn instructions formulated in natural language and formal syntax into a procedure or an optimization problem that the model must solve correctly. And the questions we want to answer the question of whether large language models can serve as digital computational models. So what we've done is essentially perhaps the most obvious thing you could think of, which is try to get them to synthesize results to track the behavior of straight line programs. We've done this with 10, 20, 30, or 40 instructions and a fixed number of variables. So the kind of example we have here, this is about as simple as you can get, right? This is good old Python, and we've got a bunch of very basic operations here, as you can see. We've actually got logical instructions along with some arithmetic and assignment operations. And we want to see how good the system is at basically keeping an accurate tally. We don't try and overburden the systems, so we keep the order of magnitude of the variables relatively small because we know that there's a detrimental effect of large inputs on the accuracy of large language models. You should try and get any large language model to multiply two large integers together and see whether you like the results. But it's interesting to see what happens. So on single instructions, these are essentially a number of large language models: GPT-3, 5 Turbo, 4, Llama, 270 billion parameter model, and a couple of others. What we look at is the ability to actually track the behavior. So we've got code snippets with solely and or and add and sub and mov. We group the results by codes of varying numbers of instructions on the x-axis and the accuracy of behavior. We have 30 simulations across a number of program types to evaluate accuracy. And essentially, you'll see huge variation in the capability of these systems, a real drop-off in terms of the size of instructions. Beyond a certain number of instructions, these systems become incapable of keeping track, and indeed return consistently increasing numbers of errors. We've kind of taken this out. I mean, I'm not going to provide all the results here. This is kind of work underway and recently submitted. But this again is another nice example where we've been looking at sorting algorithms and nested loops, where the computational complexity affects the ability of these systems to respond accurately. And again, you can see that you get quite dramatic fall off as computational complexity increases here even in the best models we have available at the moment. They get beyond quadratic, and you're in real problems. Okay, so we think that this is a very interesting way of trying to understand the actual inherent capabilities of these large language models. Why should this matter? Well, the other thing that some colleagues at Oxford have been looking at is it's not just the accuracy of performance, but whether in a world where increasing amounts of the data on which you might train these systems is generated by machines themselves, could that cause a problem? This rather interesting paper from last year by Shumaliov, a colleague at Oxford, on the cursive recursion, training on generated data makes models forget, effectively demonstrates how across a wide variety of machine learning architectures, from GMMs to even variational autoencoders and large language models, you get this kind of effective deterioration. So here's an example of text outputs on a particular model, reasonably large model, affected by model collapse. So the models degrade over generations, where each new generation is trained on data produced by the previous generation. And gradually it starts to resort to nonsense. We've got other examples from their work. So model collapse, essentially degenerative learning, where the model starts forgetting improbable events over time as the model becomes poisoned with its own projection of reality. It's rather dramatic language. But here, a nice example from a Gaussian mixture model, where what is happening over generational time is it's fed the infrequent events. Essentially, it collapses the Gaussian very dramatically. And in this case, we're looking at a large language model which is being trained on the output of a previous generation of model. So trying to simulate what might happen where systems are increasingly ingesting machine-generated content using Wikitext test data set, and where you preserve more or less data from previous epochs, and by varying that, you effectively show that perplexity, the errors inherent in these models perform, increase through time. So I guess this suggests that in the world in which I'm living, in which I want to have access to a range of different techniques, a mixture of methods essentially to kind of solve the problems we might encounter, any particular large language model does not seem to be the answer to every aspect of problem solving you are interested in. Moreover, you may well want explicitly, so people would say, well, why would you ever want to run your large language model, your approximator function, as if it was a Python interpreter? Call the Python interpreter. The lesson in that, of course, is that that is exactly the way we may want to think about composing our architectures. That perhaps even thinking of the large language model as a kind of operating system for the integration of a whole range of other capacities, having the ability to have, in some sense, a strong sense of what class of techniques might be recruited at what moment in time. And I will think, given that I ought to leave some time for questions. So the need to plan, back to that Nielsen view of the world in the closed under logical deduction. there is a reason why we have found the calculus of mathematics and logic so powerful, so useful. It gives us verification and validation methods about which there isn't a matter of statistical uncertainty. You're absolutely confident in the results. When one builds a planning system, traditionally, non-linear planning system, you are linearizing through time particular sets of actions. Or indeed, when you think about common sense reasoning, the nuggets of knowledge that constitute the way in which you can expect the physics of the world to work without going through detailed simulations, but in some sense having common sense expectations. And just today, I noticed in the Financial Times, the lead story is that GPT-5, to be announced, and Meta, latest large language model, will have AI models capable of reasoning. They describe this in terms of building mental models of the world, overcoming limitations of extended statistical approximation. And that seems to me very interesting, because it suggests to me that we are going to be actually revisiting this whole set of assumptions about what elements you may need to build stable reasoning systems, not least because systems that are deployed to solve problems in the real world, whether in business or in academia, will also come with legitimate concerns about the warrants you can give to those results. How certain are we of them? What can we do with them? Which is why, of course, at the end of the day, the question that was posed in this very provocative paper on GPT-4 when it first appeared, that they could discern the first sparks of artificial general intelligence, what they actually point out is that we don't know how these systems can effectively reason, plan, and create. Why are they generally quite good, although there are limits around them? I've talked about those kinds of benchmarks that we apply that reveal the limitations. I've shown the limitations expressively and formally. How will we move to a world where actually a variety of species of AI method are actually what we need to populate a world in which we can solve the kind of problems we need to solve in physics, astronomy, biochemistry? The world in general will not submit to a particular method to rule them all. Thank you very much.
Yeah, thank you very much for a fantastic critical overview and some food for thoughts.
Okay.
Thank you very much. Here comes the first question.
Thank you for a very interesting talk. I'm going to start with a non-technical question. So as you may know, well, as you would definitely know, there have been a number of calls from various people about the dangers of employing large language models in the wild, so to speak. With these calls ranging from saying that on the one hand, at the very least, we should be responsible and cautious in how we use them, to outright calls for bans until we have a better understanding of why and how these systems actually reason and produce output in the way in which they do. So the question is, what are your thoughts on that? Where, in terms of policy, or what should we be doing?
Yeah, so this is a problem that was brought to the attention. I mean, if you go back to the Bletchley Summit last year, a number of countries getting together, this whole idea of AI safety. If you leave aside the whole issue of existential threat and just concentrate on the perhaps nearer in effects of how do you deploy an algorithm with confidence in a business context or a safety critical context, what are the provable guaranteed behaviors of these systems? And we can see that in some quite famous recent cause celeb, even with the best endeavors, even as you're trying to kind of make the system behave reasonably in one context, it goes rogue in another, in the sense that we don't approve of its output. So you'll be aware possibly of the recent Google model, Gemini, which was both a language and an image generation system, impressive in its own right, that was coerced into providing an image that was not, can we say, it was diverse in one sense, but not in it met everybody's. This was the one where it was asked to generate an image of a number of individuals in German World War II uniforms, and it produced a suitably wide set of racial individuals in those uniforms. And it's done the same with historical figures. So within hours, that version of Gemini wasn't generating images. And back at base, they're all scratching their head going, okay, we were trying to actually make this system, if you like, more culturally representative, and we've got this side effect here. And I think that this is a huge challenge, is that you are putting into the wild systems which have generally impressive capabilities, but whose accuracy and fidelity we cannot guarantee. So where do the liabilities and the warrants rest? What are best efforts? What does a sandpit look like where you could evaluate these things in advance? So both at the moment, we just last week, the US and the UK, NIST and its AI Safety Institute and the UK's AI Safety Institute declared some bilateral work to work together on exactly these kinds of evaluations. Although it's not clear that it's yes, the evaluations are important, but it's probably the standards, it's the methods for doing those evaluations that will turn out to be important, and how you, in the meantime, construct regulation and legislation to, in some sense, keep us on the right side of the behavior of these systems. Yeah.
There is a question by Yingxue, please.
I have 3 questions. Is that possible? Well, one is, you mentioned the first, you mentioned the 4 color problems, and with this, I remember that problem was proved by mathematician in 1980s, right? By using computer and so on. What was the artificial
computer assisted? Yes, if you will.
It's a computer assisted.
Yeah.
What was that being updated by AI later with a better proof, or what?
I think in that case, you'd argue that the original, mathematical proof system was a huge help. And some people would say, I think the proof ran to 140 pages. It was something extraordinary. It was a very elaborate and elongated proof. Has it been reproved more elegantly? No, not at this point. So my example there was simply to show that these methods have been used successfully on significant problems, conjectures, and particular areas of mathematical investigation quite actively.
Okay. And the second one is, you mentioned the possible collapse and the deteriorate of these algorithms when you mentioned the last. Can you give us a very vivid example of what collapse can be, what catastrophe that it can cause?
What collapse could mean? Well, I mean, I think again, we are working out what types of collapse might look like. So if you were working with a Gaussian mixture of methods model, which is one of the quite widely used method for kind of doing various forms of pattern identification, you can see that you wouldn't always build these systems to kind of simply consume their own input time after time. That there would be these dangers of a clipping of the extremes of the distribution. The case of the large language model is, in a sense, more worrying in that you might say, well, will this be a problem? Well, the problem can arise in 2 places. One is that there is a huge amount of worry that increasing amounts of content on the web is A, machine generated, and B, not necessarily verified. You might know that various platforms, Reddit, for example, in terms of submitted code, if it's AI generated, of course, who's to say whether it is or isn't, there are various rules. In fact, I think some platforms have forbidden these systems to be submitted because the worry is you basically consolidate potentially misleading exemplars. What if the entire enterprise is to poison the information well? So misinformation, disinformation, fake. We talked about this in my last talk a little bit about the construction of deep fakes in terms of scientific publications or data sets. How are you to know? And that so that's another way in which the collapse can occur. There isn't one thing. I mean, clearly, using some of these models where they simply ingest increasingly divergent content can lead to really bizarre behavior, as we saw in the first slide there. But in other cases, it's a more subtle form of collapse where the trust in the information environments that's being used to train these systems collapse. I mean, there is talk of a pre and a post large language model era when at scale, the information assets were not tainted. The other aspect of this, of course, is that we know a rough scaling heuristic is that you need about twice as many tokens to train these systems on as there are parameters in the model. Now, there's also interesting work that shows that you don't have to keep indefinitely scaling, but you can have some quite lean, moderate-sized models that perform pretty well, actually. But in the race for sheer size, the content out there isn't quite sufficient. So the notion that, oh, let's just use some synthetic data, okay, let's just absorb a lot more machine-generated content is in play, and what will that actually mean is the question.
And the last one is that you mentioned the OpenAI and the Meta is now developing the GPT-4 and 5, etc., and they will advance this whole thing with more reasoning of this. And then also you said this kind of high-level AI is actually when we look at it, is no more than just a whole bunch of simple logic and so on. So this is really a complex thing. And do we understand it? And also, can this kind of mimic what happened in humans' brain and we would reasoning from our biology?
This really intrigues me because in some sense we are clearly a biochemical statistical machine that is running in very different ways to the architecture of these large language models, very power efficient, very densely connected, very using all sorts of topologies we don't include in our large language models yet. But the interesting thing here is the extent to which in prosecuting and developing our science, we and also in the way that we developed our philosophy, our literature, we conceptualize the world, that we have in fact blocked the world up into words. We've developed systematic calculuses, and we can argue about the philosophical origin of mathematics, whether you're an intuitionist or whatever you are, that in some sense we developed symbol manipulation systems with huge power, generatively, many of them closed under deduction, so we know exactly what the qualities of these systems is in terms of their computational properties. And that's an invention that we have layered in some sense on top of ourselves. And this is maybe something that we'll begin to see emerging in our large language models, that for the sake of memorization, for the sake of model management, memories will get constructed. What will they be like? Will they start to have the stability properties of things like human conceptualizations or models where you, in some sense, keep the track of the tally, or a planning system which explicitly has sets of operators that manage the sequencing of events through time. And you essentially remove the statistical uncertainty by having another module which is reasoning in that way. How they've done that, how they propose to do that in their different approaches. Of course, again, interestingly, different companies are more or less committed to open access to the models and the techniques, which is, again, an interesting place as researchers in computer science to be, which is that how do we make a virtue out of this necessity to kind of work out what could be going on, what should be going on, to test and evaluate these systems.
There was a question here by Zurab. Zurab, please.
This question actually relates slightly to how you answered the previous one. So I think that one thing that's missing, but maybe you will tell me that it's not missing, it's already there, is a system that checks what the AI outputs. A very simple example is if you ask a mathematics student to solve a problem, very often the first attempt has many errors. But when the student rereads this attempt themselves, they themselves even find the mistakes often, or don't understand what the work was. And so even for the calculation of large numbers, why don't they already now incorporate a simple calculator that can check these kinds of answers?
Well, that is exactly, I would suggest, one approach is to have this mixed methods model. I think in a sense, of course, the striking thing is that for quite a swathe of tests, particularly in what we've traditionally thought of as language understanding, comprehension, reading tasks, the system, because of this huge corpus of ingested content, does a job which you can interpret as being plausible. It's when you take them into these formal calculi models that things become more problematic. So why wouldn't you help yourself to an integration, a hybrid architecture in some sense? So the system knows it can't, and in fact, the system will declare that in some context. I mean, that's the way they're kind of formulating this. Having said that, of course, where you're looking for deep patterning across extended structures, again, having these systems look at encodings where the encodings aren't language, but they are molecular structures, for example, genomic sequences. You know, the human is looking for potential suggestive patterns, correlations. So it will depend on what your demands are, I think, about the nature of what a successful answer is. And that's critical. In some areas, you will not want to be uncertain. And if you have a system which can render certainty in that domain, why wouldn't you appeal to it? Yeah.
I think we have a few questions from our online audience. I don't know, would you like to, Donovan, to guide us through some of those at least?
I can read the first one. Okay. How should we adapt education and training programs to prepare the workforce and research for the AI-driven economy of the future?
Well, not everybody is going to be an expert on transformer architectures or data science. Some will, of course, and some of those people are in this room now. But it would seem to me that one of them is to instill a healthy sense of when we talk about the co-pilot, the Microsoft model, which is powerful, I think, in some ways and suggestive. The essential thing is preparing people for the fact that these systems are not omniscient, and nor are they completely correct in all conditions. So you have to have a user understand why they should be an informed skeptic about anything they are being given. Not anything. So I think the position of understanding, at least the digital literacy you need to understand something about the nature of how these systems obtain their information, how they are. People understand from the very fact that when you get your blasted text completion, it's always picking the wrong word, and off you go. You haven't noticed it, but you've texted it off with a completely silly pick. And they know something about the probability of the possibility of error. And I think that is a hugely important thing to instill. But more generally, to the question of how do we prepare, we, I think, have to, in the same way, digital literacy isn't just about the recommendations. It's about understanding the data ecosystem, which is supporting this, the possibility for representation. The fact that we can make simple demands. Again, in an educational context, the thing that a lot of institutions worry about is how are we going to stop these systems just becoming the world's best plagiarizers, Well, actually, we've got a well understood and codified set of methods for dealing with citation. There is a new sense in which we have to adopt a very old adage, which is a thing should say what it is and be what it says. And so that we have to come up with some set of reasonable conventions about how we include this information in our learning. And we know already that teachers are incorporating these tools extensively to help in everything from lesson planning to some forms of evaluation. Yeah.
Thank you. Maybe Donovan, maybe one more lesson. I have a question from the online audience because I'm concerned about the time now.
So this one's a bit more specific towards your group. The computational requirements for training and evaluating LLMs are very huge. How is your research group taking care of this for your LLM studies?
It's challenging, right? So we, I think, along with a lot of researchers in universities in this area, of course, resources are distributed unevenly, and of course, some people will have access to the kind of high-level compute. But you can do a lot on, as I say, mid-scale models which demonstrate the principle. Okay, might isn't everything. I would say that when we do our evaluation work, you'll notice that we were plotting work against GPT-4, which is, at the top end of behaviors out there at this moment in time. So what we can do, of course, there is use them as tools. What we can do, of course, with our open source tools is be much more explicit about getting inside and understanding what the actual configuration parameterization really does to this spec. So I think it calls for a little bit of a different relationship ultimately between ourselves and some of those in industry who are doing this research. The idea that, well, we're just the poor cousins and our job is to offer up our best students to go and work for them. I think we need and I'm not saying that people think like that, but that would be really unfortunate if a generation of students thought the only place I can do serious work is the very most powerful hardware. There are some problems where that may be true. Then we need to form the alliances. Interesting thing about this latest bilateral between the UK and the US is that the commitment from the big participants, the big platforms, is to give us direct access to those models in an unfettered way for particular purposes. Yeah.
Thank you very much. Then let's thank Sir Nigel very much for his very nice presentation.